Okay, today we'll go over basic concepts of probability. So starting with these definitions, what is an event, simple event, and sample space. Okay, so let's take rolling a die, single die, for example. So an event is any collection of results or outcomes. So for example, like rolling an even number is an event, right? Or rolling a number that is greater than 5, that's an event. Well, what is a simple event? Is an event you can't break down further. For example, rolling with the outcome of 5, that's a simple event. You can't break it down further. But rolling a die with a number, with an even number, that's not a simple event because you can break it down to rolling it down with the outcome of 2, 4, 6. Right? That's why rolling a die with even number is not a simple event, but it is an event. Right? So sample space in this case will be having an outcome of 1, 2, 3, 4, 5, 6. That's all the possible outcomes. You can't have any outcomes that's other than B6. So this is called sample space. Any questions so far?
No.
Okay, so those are the definitions. All right. So having a single birth, having the result of having one girl, that's a simple event, right? The sample space here is you're either having a boy or a girl. So sample space has 2 elements in it, like over here. But if you're giving birth to 3 kids, or you're having 3 births, having 2 boys and 1 girl, that's an event, but it's not a simple event because this can break down into first one boy, second boy, third one girl. You know, having 2 boys and 1 girl, either the girl is the last one, or the girl is the middle one, or the girl is the first one. Right? 3 possible simple events for this event of having 2 boys and 1 girl. Okay, so here is the sample space. Let's break it down here. Why do we have such a long list for sample space? First of all, if your first kid is a boy, right? So here we have several cases. First is your first is a boy, second is also a boy, and third is also a boy. This is one case. Second case, first is a boy, second is a boy, but the third one is a girl. Okay. And another case is first is a boy. Okay. Second is a girl, and third one is a boy. So let's do it like this. The first one. 2 possibilities. First one is either a boy or a girl. For the second one, if your first one is a boy, the second one is either a boy or a girl. Right. Forget about this. And if you first one's a girl, the second one is either a boy or a girl. Okay, then the third one. If your first one and the second one is a boy, the third one is either a boy or a girl. So here we have 2 cases, 2 single events. If your first one is a boy, second one is a girl, the third one is either a boy or a girl. So you break it down into these 2 events. I'm making this a mess here. And if your first one is a girl, second one is a boy, either the third one is a boy or the third one is a girl. And the last branch can break up into 2 cases too. The third one is either a boy or a girl. So altogether, if you have 3 births, the sample space has how many elements? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. All right. 8 possibilities. Any questions here?
No.
Okay. All right. So, notation for probabilities. P denotes probability, and A, B, C are letters we use to denote events. So PA here means the probability of event A occurring, and for any probability, it should be a number between 0 and 1. The probability of the event is equal to 0 when the event is impossible to happen, right? And the probability of an event is equal to 1. That means that event is for sure happening. 100% is happening. Questions on this part?
Nope.
Okay. So several ways to find probability. One is called classical approach. So here we're talking about cases like we throw a die and we assume the probability of getting each outcomes are equal, like is equal. The probability of getting 1, 2, 3, 4, 5, 6, they're all equal. And so we assume event A has S different ways, then the probability of A happening is equal to S over N, which is the different numbers of simple events. So let's give you an example. I let A be an event, let's say throw a dice and having an outcome of even numbers. Okay, so how many ways would you have for even numbers when you throw a die?
3.
3, right? 2, 4, 6. So
Yep.
3. And out of the number of different simple events, that will be
3 out of 6.
6. So 1/2. The probability of throwing a die and get even numbers is 1/2. Something like that. Right. So classical approach. All right. Question?
Nope.
Okay. Now let's look at this example. Which of the following are probabilities? Is 0, can 0 be a probability?
No.
Remember, for any event A, the probability of A could be a number equal to 0. That just means A will never happen, right? So a probability could be a 0. It could be 1. And any number between 0 and 1, right? So you could have an event with probability of 0. That just means that event will never happen, right?
Okay.
Okay, so we could have 3 over 5.
Yes.
Yes, that's a number between 0 and 1. So this is good. How about 5 over 3?
No.
No, that's greater than 1. That's why it's no. Negative 0.25.
No.
No. 250%?
Definitely no.
No. 7 over 3?
Nope.
That's not a probability. 1?
Yes.
Yes.
Yes, we can have 1, right? That means that event is for sure happening. 50, I'm not sure what it is. 50-50? That's not how you represent probability.
I was going to say, wouldn't that be half?
Well, then you will write 1/2.
Okay.
Or, this doesn't represent a probability, but there's a 50-50 chance. We say that all the time, right? That means you have a probability of 1/2 or 50%. Okay, so 5 to 1.
Nope.
No ratio, not. This one.
Yep.
Yes.
Yep. And this one,
Nope.
not greater than 1. Okay, that's it. Okay. All right. Well, let's look at this problem. It's kind of who discovered penicillin, and these names, champagne, blah blah blah. 1, 2, 3, 4, 5. These 5 names. If you take a random guess for the answer to that question, what is the probability that your answer is the correct answer of Alexander Fleming? Well, I didn't know that. But if you take a random guess, what will be the probability of guessing it correctly?
1 out of 5.
1 out of 5, right? There's only one correct answer out of 5 answers. Right. This is classical probability approach. Are we good with this kind?
Yes.
Well, I'd like to look at some of the boy-girl situation. Okay. So let's look at number 1, for example. So assume that boys or girls are equally likely. Well, I heard like girls are slightly more likely to happen, but anyway, assume that boys and girls are equally likely. Find the probability that when a couple has 3 children, there's exactly 1 girl. How do we find that?
Well, by looking at that chart, when you do the boy, boy, girl, all of that, and then there were 8 possibilities. There's only 3 times you can get it.
Okay.
So 3 out of 8.
We're talking the chart there, and yeah, well, that works.
That's the way I do it.
Well, if
I'm
you,
more visual.
So we could list all of them. Like, let me
yeah,
go.
boy, girl, boy, boy, girl.
We can list all of these.
Yeah.
Right, and then you find, okay, the probability of having 1 girl, well, 1 is here, 1 is here, and the other one is here. That's all the cases, right?
Yeah.
So that would be 3 out of 8. That's one way to look at it. Another way to see it is, so you're having 3 births, right? And for the first kid, there are 2 probabilities, right? Either a boy or a girl, right? At the second birth, you have 2 probabilities, and the third birth, 2 probabilities. So multiply them together, 2 times 2 times 2, you have overall 8 outcomes. So that's something over 8, right? And how many? So you want only 1 girl, exactly 1 girl. So that 1 girl could be the first kid, could be the second kid, could be the third kid. So here we have 3 cases, 3 out of 8. Either way, right? Or you can list everything. Okay, so number 2 here, find the probability that when a couple has 3 children, there are exactly 2 girls.
So it will be something over 8 for sure.
Yeah, something over 8. What over 8?
Two. It's not 6. I don't think it's 6.
No. So the way you could make a chart and count, right?
Yeah, that's what I
Or another way to think of it would be having exactly 2 girls means having exactly 1 boy, correct?
Yeah.
So that boy can be the first kid or the second kid or the third kid. So here we have 3 cases, 3 out of 8. So exactly the same as having exactly 1 girl out of 3 births.
Okay.
Okay. Okay, this one's more. Okay, identify the sample space for a couple having 4 children. And then find probability of getting 3 girls and 1 boy in order.
So that would be
take the
something
list.
over
The list
16,
is,
right?
the list is long. Let's not make the list. Just find the probability of getting 3 girls and 1 boy.
So would we be able to use your
Yeah,
calculation?
good.
So that would be 16 then. Something
Yeah.
over 16.
Yes. So you will have 4 children. The probability of having the first one, you will have 2, choices for the first one, 2 choices for the second one, 2 choices for the third one, 2 choices for the fourth one. So in your sample space, you're supposed to have 16 elements in it.
Mm-hmm.
So something over 16. Getting 3 girls and 1 boy would be how many simple events? That event.
Wow.
Well,
I would have to write it out.
yeah, I wrote it out, even though that's longer because I don't know how to do the shortcut. I was thinking off my head without doing a shortcut. I'm thinking to myself 4/16, but you could reduce that.
Well, it is 1 boy, right? Yeah.
Yeah. Oh, yeah, that's 1 boy. I'm thinking girls. See, yeah, 1 boy. 1.
So if it is 1 boy, like what we did earlier, that 1 boy, there are only 4 cases, right? Either that boy is the first kid, or the second kid, or the third kid, or the fourth kid. Only these 4 cases, correct?
Yes, but I thought you couldn't accept an even number.
So it would be 4/16, but you would reduce it, right?
Yeah, so 1/4.
I was right. In my head, I knew I was. Okay. It's a lot easier, but I always, like you do, I have to figure, I went girl, girl, boy, girl, it takes longer, but.
The list, you could say, okay, the first kid, you could either be a boy or a girl, and then
But if you have 4 children, you have 4 shots of having a boy. It's 50-50.
Then boy, girl, like keep going, girl.
Yeah, you can go off the page.
Girl, yeah, and then third, just keep going. Then you will have 8, and then fourth, you will go to 16 here. Just keep going. Okay. And then you have 16 cases. Then you count, right? How many of them are 3 girls and 1 boy? It will be 4. Okay.
Yep.
All right. Moving to the next one. Okay. The second way to find probability is through basically observation. So sometimes we don't know the probability of some events, so we have to, based on some data we collect, and find the probability of that. So the probability of the event A here is equal to number of times A happened divided by number of times the procedure is repeated. Okay, so how does it work? Let's look at one example. Okay, so here it says, in a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in death. Now, I always thought I would be the one of the 21. If I do skydiving, so never dare to do that. Anyway, so what is the probability of having a skydiving and end up in death? Well, here you can say probability of having skydiving and death and end up being death is number of skydiving in death, which is 21, divided by the overall number of skydiving jumps, which is end up to be 0.0007. Okay. Questions on this?
Nope.
Yeah. Just based on observation or based on data. Okay, so let's look at this problem. Here it says, in a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during the same time period. If a high school driver is randomly selected, find the probability that he or she texted while driving. So how do we find that probability?
Well, you would add both of the numbers,
Together.
the ones that texted and did not.
Yes, so when we add them together, that will be the total of people driving. Okay, texted and not tested. And so what will be on top?
The ones that are not, 3,785.
So we want to find probability of somebody who texted, right? So it's 3785. Whatever that number is, I won't do the calculation here. Just whatever that number is. Good here?
Yep.
Okay. All right. Complementary events. So the complementary event of event A, denoted as a bar here, and means the all outcomes of event A that does not occur. So say I'm throwing a die, right? And event A means you are having an even number. So A bar here will represent the event of throwing a die and having an odd number. That's it. So that means not A. Basically, you're throwing a die and not getting an even number. That will be A bar. Throwing a die and getting an odd number. Okay? I'm making myself clear here?
Yep.
Okay. So the probability of A plus the probability of A bar or A complement is equal to 1. So for example, here the probability of getting an even number when throw a die plus the probability of getting the odd number when throw a die should be equal to 1. Right? So the probability of A plus the probability of not A should be equal to 1.
Okay.
Okay, that's easy to understand. Okay, so here it says, in a recent year, there were 3 million skydiving jumps, and 21 of them result in death. Find the probability of not dying when make a skydiving jump. That would be, well, there are 2 ways to do it, right? One way is you have the 3 million at the bottom. On top, you will do 3 million. How many zeros? Yeah. Minus 21.
That's the way I did it.
There's another way, which is you use 1 minus whatever you got earlier, 0.000007. If that's enough zero. Let's just say this is the right answer. So this number would be the probability of having a skydiving and not dying. Okay. Right. So basically, 1 minus 21 divided by 3 million. So figure out whatever this first and then use 1 to subtract that. Okay?
Okay.
All right. All right. So another example real quick. Say my event is throwing a die and get the outcome of 5. Right? So okay, that's my event A. So what is the probability of A bar? Or the complement of event A?
I'd almost say 10, but I know it's not 10.
Well, what is the probability of throwing a die and get the outcome of 5? Throw a die and get a 5.
1 in 5? Or sorry, 1 in 6?
1 in 6, right? 6 possible outcomes and 5 is one of them. So the probability of not A, or the probability of throwing a die and not getting 5 would be?
5 over 6. 5, 6.
Yes. So 1 minus 1, 6. 5 over 6. Okay?
Yeah.
Okay. All right.